January 28, 1986, Kennedy Space Center, Florida. Icicles are hanging off the launch tower, and inside Space Shuttle Challenger, 7 people are strapped into their seats, waiting. 73 seconds after liftoff, they will be gone. Not a bomb, not pilot error. A ring of rubber about a quarter of an inch thick got too cold to do its job. Here's exactly how that was allowed to happen. To understand January 1986, you have to understand how boring spaceflight had become. The space shuttle had flown 24 missions in under 5 years. It launched satellites, carried laboratories, and landed on a runway like an airliner. NASA had sold it to Congress as a space truck. Reusable, routine, eventually flying dozens of times a year. By 1986, the major American television networks had mostly stopped carrying launches live. Space was no longer news. That was exactly what NASA wanted. Mission 51L was supposed to be the flight that made people care again. Challenger, Orbiter, OV-199, was the fleet's workhorse, about to fly for the 10th time. On board, Commander Dick Scobie, a Vietnam combat pilot, Pilot Michael Smith, mission specialists Judith Resnick, Ellison Onizuka, and Ronald McNair, payload specialist Gregory Jarvis, and a 37-year-old high school social studies teacher from Concord, New Hampshire, named Krista McAuliffe. McAuliffe had been selected from more than 11,000 applicants for the Teacher in Space project. She was going to teach 2 lessons live from orbit. NASA piped the launch feed into American schools for free. So on that morning, children across the country were sitting cross-legged in front of classroom televisions, waiting to watch their teacher fly into space. Now look at the machine underneath them. The orbiter didn't lift itself. Bolted to that orange external tank were 2 solid rocket boosters, each 149 feet tall, about 45 meters, producing more than 80% of the thrust at liftoff. And a solid rocket has one property that defines everything that follows. Once it is lit, it cannot be throttled, and it cannot be shut down. It burns until it is empty. The boosters were built by Morton Thiokol in the Utah desert. They were far too large to ship whole, so they were made in segments, hauled by rail to Florida, and stacked together at the Cape. Where those segments met, engineers created something called a field joint, a steel lip slotting into a steel groove, and sealing that seam against roughly 3,000 pounds per square inch of burning propellant were 2 rubber O-rings, each one about a quarter of an inch thick, each one roughly 37 feet around. 2 rings of rubber. That was the barrier between the fire and the sky. And in 1977, 9 years before this launch, a NASA engineer put a warning about that exact joint in writing. He was overruled. What he predicted is precisely what happened. The joint was supposed to work like this. Internal pressure pushes the primary O-ring into a gap. The rubber squeezes into the space. The seal holds. Simple. Proven. The design was adapted from the Titan III rocket, which had flown for years, but the shuttle's version was not the Titan's version. In pressure tests at Marshall Space Flight Center in 1977, engineers watched the joint do something the Titan joint never did. Under pressure, the steel walls flexed apart. The gap the O-ring was supposed to fill got wider. At the exact instant the seal was needed most, they called it joint rotation. Marshall engineer Leon Ray and his colleagues recommended the joint be redesigned. Management disagreed. The seal was declared acceptable, and the shuttle flew. At this point, the disaster was still 15 years away and entirely preventable. But the next warning came from the hardware itself. November 1981, Mission STS-2. When the boosters were recovered from the Atlantic and disassembled, technicians found something disturbing. Hot gas had gotten past a primary O-ring and eroded the rubber. It hadn't burned through, but it had burned into it. That should have grounded the design. Instead, it started a habit. Erosion was measured, tabulated, compared against margins, and filed under acceptable risk. In December 1982, The joint was formally reclassified Criticality 1, NASA's own designation, meaning that if this single component failed, the result was loss of vehicle and loss of crew, with no backup. They kept flying it, 16 more times. Then came January 1985. Mission 51C launched after a Florida cold snap at 53 degrees Fahrenheit, about 12 Celsius, the coldest shuttle launch to date. When those boosters came back, engineers found the worst damage they had ever seen. Black soot blown clean past the primary O-rings on both boosters, deposited between the primary and secondary seals. Hot gas had reached the last line of defense. Thiokol engineer Roger Boisjoli went to Florida, examined the joints himself, and came to a conclusion that would define the rest of his life. Cold rubber doesn't spring back fast enough. In the cold, the seal is late, and being late by a fraction of a second is the whole difference. 3 months later, in April 1985, a nozzle joint on Mission 51B did something worse. The primary O-ring eroded completely through. The secondary O-ring, the backup, eroded too. A single seal on a Criticality 1 joint had failed in flight, and only the last barrier stopped it. In July 1985, NASA imposed a formal launch constraint on the booster joints. A launch constraint means the vehicle is not cleared to fly. It was waived, and then waived again and again, 6 times in a row for 6 consecutive missions, right up to Challenger. That same month, Boisjoli wrote an internal memo warning that if this was not fixed, the program stood to lose a vehicle and its crew. Nothing changed. Why not? Because 1986 was going to be the year the shuttle proved itself. 15 flights were on the manifest. There was a comet to observe, a president's State of the Union address that evening, and a teacher who was already famous. Missions slipping meant money and credibility slipping with them, and 51L was slipping badly. Launch was postponed from January 22nd to the 23rd to the 25th to the 26th. On the 27th, a hatch handle jammed and had to be sawed off, and by the time it was fixed, the crosswinds were out of limits. 4 scrubs. The press had started using the word jinxed. Then the forecast came in for the night of January 27th. 18 degrees Fahrenheit, -8 Celsius. Colder than anything the shuttle had ever launched in, by a margin of 15 degrees. That evening, a teleconference connected 3 locations, Thiokol in Utah, Marshall in Alabama, and Kennedy in Florida. Boisjoli and engineer Arnie Thompson presented their data and made a formal recommendation. Do not launch below 53 degrees Fahrenheit. The reaction from NASA was not gratitude. One senior manager said he was appalled. Another, Lawrence Malloy, asked the question that has been quoted ever since. My God, Thiokol, when do you want me to launch? Next April? Pretty good. Thiokol asked to go offline and caucus. They said 5 minutes. It took about half an hour. Inside that room, the engineers held their position. But the pressure inverted the normal rule of spaceflight. Instead of proving it was safe to fly, they were now being asked to prove it was unsafe. Senior Vice President Gerald Mason turned to Engineering Vice President Robert Lund and told him to take off his engineering hat and put on his management hat. The vote was taken among 4 managers. Not one engineer signed it. Thiokol went back on the line and recommended launch. And the 7 people who would be sitting on top of that rocket were never told the conversation had happened at all. Overnight, water lines on the pad had been left trickling to stop them freezing. By sunrise, the launch tower was hung with ice. The ice team counted icicles up to 16 inches long. Launch slipped 2 more hours while the sun did what it could. Remember what this whole flight now depended on: 2 rubber rings sealing a single joint on a single booster. The crew boarded at around 8 a.m. and sat in the cold for nearly 3 hours. Air temperature at launch was 36 degrees Fahrenheit, 2 Celsius. On the shaded right-hand booster, the aft field joint was later estimated to be as low as 28 degrees, below freezing. The rubber in there was not a seal anymore. It was effectively hard plastic. 11:38 a.m. Eastern, ignition. At 6:78 seconds after ignition, a puff of dark gray smoke escapes the aft field joint of the right booster. 8 more puffs follow in the next 2 seconds. Nobody in mission control sees them. Nobody watching sees them. They will not be found for weeks. The primary O-ring has already failed. What temporarily saves them is an accident. Aluminum oxide from the burning propellant packs into the breech and plugs it. A seal made of ash. For 36 seconds, the flight is textbook. At 37 seconds, Challenger enters the most violent wind shear any shuttle had ever flown through. The vehicle's steering system fights it, correcting hard again and again. The plug of ash shakes loose. At 7:88 seconds, a tracking camera records a small flame on the side of the right booster. It is pointed at the external tank. At 262 seconds, it is a continuous, well-defined torch burning at roughly 500 degrees. At 660 seconds, the flame changes shape. It has burned into the external tank, and liquid hydrogen is now feeding the fire. At 68 seconds, Mission Control transmits the routine call to increase engine power. Commander Scobie answers, "Roger, go at throttle up." It is the last transmission from Challenger. At 20 seconds, the strut holding the bottom of the right booster to the tank burns through. The booster swings free at the top and pivots into the tank like a battering ram. At 124 seconds, the hydrogen tank ruptures. At 162 seconds, at 48 feet and nearly twice the speed of sound, the entire vehicle disintegrates. Here is the correction the footage never makes for you. It was not an explosion. The hydrogen and oxygen burned, but what destroyed Challenger was aerodynamic force. The vehicle turned sideways into a supersonic airstream and was torn apart in a fraction of a second. On the recorder in the crew cabin, at 63:62 seconds, pilot Michael Smith says 2 words, "Uh-oh." In the grandstands, Krista McAuliffe's parents are looking up. For several seconds, almost nobody understands. There is no bang, only that white forked cloud, and the 2 boosters corkscrewing away on their own. Public Affairs Officer Steve Nesbitt keeps reading telemetry, then stops and says the sentence that ended the routine era of spaceflight, obviously a major malfunction. At about 110 seconds, the range safety officer destroys the 2 runaway boosters, and the crew cabin, torn free but structurally intact, keeps climbing. It reaches roughly 65 Zollzurn feet before it begins to fall. It falls for 2 minutes and 45 seconds. It hits the Atlantic at around 207 miles per hour. Everything about what happened inside that cabin during those 2 minutes and 45 seconds would remain unknown until investigators recovered a specific set of switches. We'll come back to that. On February 3, 1986, President Reagan appointed a commission chaired by former Secretary of State William Rogers. Its members included Neil Armstrong, astronaut Sally Ride, test pilot Chuck Yeager, and a physicist from Caltech named Richard Feynman. The search became the largest salvage operation NASA had ever run. Ships, submersibles, and sonar dragged the Atlantic seabed for months. On March 7th, divers located the crew cabin in about 100 feet of water. In April, they brought up a section of the right-hand booster's aft field joint with a burn hole through the steel, but the answer had already been found on film. NASA's tracking cameras had captured the launch in extraordinary detail, and when analysts went frame by frame, there it was, black smoke at 678 seconds. Not from the engines, not from the tank, from one joint on one booster before the vehicle had even cleared the tower. Then came February 11th, a televised hearing. Feynman, who had been quietly briefed on the cold weather problem, asked for ice water. He took a sample of O-ring rubber, clamped it, dropped it into the glass, and left it there while the hearing continued. Then he pulled it out and released the clamp. The rubber stayed squashed. For several seconds it simply did not spring back. An entire national investigation collapsed into one image that a child could understand. Cold rubber is slow. The joint needed the seal in milliseconds. It didn't get it. But here is where the story stops being about rubber, because the O-ring did nothing wrong. It behaved exactly as its own physics said it would, exactly as engineers had predicted in memos dating back 9 years. The rubber was not the failure. The rubber was the messenger. The real finding of the Rogers Commission was about how the decision to launch got made. A joint classified criticality 1, no backup loss of crew, had been flying under a formal launch constraint that was waived 6 consecutive times. Damage that appeared on flight after flight had been reclassified, one report at a time, from warning sign to expected behavior. Sociologist Diane Vaughan later gave that process a name that is now taught worldwide, the normalization of deviance. Nothing goes wrong, so the abnormal quietly becomes the standard. And then Feynman found the number. He asked NASA managers and NASA engineers separately the same question: what is the chance of a catastrophic failure on any given flight? Management's working figure was roughly 1 in 100,000, which would mean launching daily for close to 3 centuries without losing a vehicle. The engineers who actually built the hardware estimated something closer to 1 in 100. The two halves of the same agency disagreed about the risk of killing a crew by a factor of 1,000. Feynman's dissenting appendix ended with a line now carved into engineering ethics courses: reality must take precedence over public relations, for nature cannot be fooled. And the switches. Each crew member had a personal air pack activated by hand. When the recovered packs were examined, at least 3 of the 4 found had been turned on. Michael Smith could not have reached his own. It was mounted behind his seat. Someone else reached back and switched it on for him. Investigators could never determine whether the crew stayed conscious all the way down, but at least some of them were alive and thinking and helping each other after the vehicle came apart. The shuttle did not fly again for 32 months. The booster joint was completely redesigned. Engineers added a capture feature, a steel lip that physically prevents the joint from rotating open under pressure. They added a 3rd O-ring, and they wrapped the joints in electric heaters so the seals could never again be launched cold. More than 100 other changes followed. NASA created an independent Office of Safety, Reliability, and Quality Assurance, reporting outside the chain of command that had waived the constraint. Astronauts were moved into senior management, so the people who flew had a voice in whether the vehicle flew. Launch commit criteria gained hard temperature limits, in writing, unwaivable. A crew escape system was added, a pole for bailing out in controlled gliding flight, which would have saved nobody on 51L and which everyone knew. On September 29, 1988, Discovery launched on STS-26. The shuttle flew for another 23 years. But the lesson that outlived the hardware isn't in the metal. Every time anyone in any industry says, "We've seen that before and it's always been fine," this is the accident that argues back. That sentence is not evidence of safety. It is often just evidence that you have been lucky and that you've stopped counting. NASA learned it. And then, in February 2003, Columbia broke up over Texas, killed by foam strikes that had been observed for years and reclassified as acceptable. The investigation board wrote that the cultural failures behind Challenger had never actually been fixed. The same disease, 17 years apart, 14 people in total. Roger Boisjoli never worked in the rocket industry again. He spent the rest of his career giving lectures to engineering students about the night he was right, and lost the argument. He said the thing that haunted him wasn't that nobody listened. It was that he stopped pushing. 73 seconds, 7 people, a quarter-inch of rubber, 37 feet long. That was simply too cold to move in time. The tragedy of Challenger was never that the flaw was hidden. It's that it was written down, filed, measured, discussed, and flown anyway. 24 times until the morning the weather stopped forgiving it. There are other disasters where the fatal detail was even smaller and even better documented. If you want those, subscribe, and I'll take you through them one failure at a time.